Hi, I'm Leticia Corral from Mexico, and I'm going to present my work, Supermassive Black Holes Entropy Formula, a Dimensional Analysis. The agenda: introduction, modeling results, forthcoming research, conclusions, and references. The objective was to develop a formula in dimensional analysis using the constants of nature in order to measure the entropy during the evaporation time of different types of black holes of Schwarzschild, Reisner-Nostrom, Kerr-Newman, and the remnant black hole of the binary black hole Messier GW, the 14th of September 15, GW, the 26th of December 15, and the LTV, the 12th of October 15, detected by the Laser Interferometer Gravitational Wave Observatory LIGO, and thus quantify the quantum effects involved in order to contrast this formula with the Bekenstein second generalized law of thermodynamics. From the results obtained, we can conclude that this formula could have some relationship with the detection of the Charus image of supermassive black holes that just on April 4, 2019, the Event Horizon Telescope managed to reveal the first image of Messier 87 supermassive black hole. This is the formula in dimensional analysis that contains all these terms. This formula manages to join three different fields of physics, such as the thermodynamics, general relativity, and quantum mechanics. This formula contains the time of evaporation calculated with this mathematical relationship that include the constant of nature and the mass of the black hole. This formula also contains the thermal Hawking radiation at Hawking temperature by means of this relationship that contains the constant of Boltzmann, surface gravity, and event horizon area with the three parameters of the black hole, such as the mass, angular momentum or spin, and the electrical charge. According with Bekenstein, 1974, we suggested that the generalization of the second law of thermodynamics for a region containing a supermassive black hole is such that the entropy plus common entropy of the black hole exterior never decreases. We equate our formula with the generalized entropy according with the Bekenstein generalized law of thermodynamics that contain the entropy during the entropy with the Bekenstein-Hawking formula included. These are the metrics used in this work. In this slide, I show the metric tensor of Schwarzschild, Reisner-Nostrom, Kerr-Newman, and its corresponding energy stress tensor calculated in general relativity. This is an analysis of the entropy formula. For supermassive black holes at the limit when thermal Hawking radiation at Hawking temperature tends to absolute zero, the rate of change of the entropy generated during its evaporation time and eventual disappearance when the temperature tends to zero, the result is the value of minus floor infinite. In the same way, this rate of change with respect to the time is floor undefined. Floor infinite represents a flooring point infinity. This value is used to indicate a flooring point value that is too large to be otherwise represented. Meanwhile, floor undefined represents a non-numeric object in the flooring point system. This value can be returned by a function or operation if the input operands are not in the domain of the function or operand. On the other hand, supermassive black holes of Kerr, Reisner, Nostrom, the remnant black hole of 3 different binary black hole mergers studied here have temperatures that tend to absolute zero, especially the former ones. At the limit, when the entropy during the evaporation time and its rate of change with respect to the time when time tends to zero, we obtain in both cases the same result of flow undefined, which means that the supermassive black holes are not primordial black holes as we expected. On the other hand, at the limit, when the entropy during the evaporation time and its rate of change with respect to the temperature, when temperature tends to infinite, we found the same result of zero, which means that for supermassive black holes tend to cancel in this critical case when temperature tends to infinite, as it could have happened at the Big Bang as we expected. This analysis of the entropy formula satisfies the third law of black hole mechanics and third law of thermodynamics. These figures show calculations for entropy during the evaporation time, entropy with the Bekenstein-Hawking formula and its corresponding event horizon areas, the time of evaporation, the surface gravity, and the thermal Hawking radiation at Hawking temperature, in which we used LIGO astronomical databases of the remnant black hole of 3 different binary black hole mergers studied here. Calculations were made with different parameters of mass, angular momentum or spin, and electrical charges. According with the black holes laws of black hole mechanics from Hawking's physics. In all cases, thermal Hawking radiations tend to increase as the mass evaporates, generating an increase in the ordinary entropy outside of the black hole, results that are agree with other authors that have been studied the thermal atmosphere outside of the black hole. Such authors are Bardeen, Bekenstein, Sorkin, Thorne, Unruh, and Wolf. There are some important results in this work that are agreed with these authors, such as the generalized entropy of the state of the region outside of the black hole that always increases, and the entropy during the evaporation time and its event horizon area always decreases individually, but the total entropy always increases. On the other hand, Kerr-Newman calculations with the material content of the energy stress tensor of the order of 4.5 per 10 to 10 kilograms using the cosmological constants and results of other authors for spin and electrical charges such as 0.7 for spin and 0.2 and equal to mass for electrical charges. We found results for the type of evaporation of this type of supermassive black holes of Kerr-Newman of the order of 2,400 years, which perhaps correspond to a primordial black hole. And there are one relationship very important made by Stephen Hawking that related the 3 parameters of the black hole with the constant of the nature that in this case indicate that the 2 event horizons disappear, but non-zero surface gravity indicate that they are not destroyed and therefore do not leave the naked singularity according with Penrose's cosmic censorship conjecture. These figures show the entropy during the evaporation process versus thermal Hawking radiation at Hawking temperature calculated with the two collaborations of Abbott et al. Detected by LIGO and modeled with the metric of Kerr and Reisner-Nordstrom that satisfy the Bekenstein's second generalized law of thermodynamics. These are some of the most important results in this work. We can see that for a Schwarzschild black hole of a solar mass, the time of evaporation is of the order of 10 to 64 years, much older than the age of the universe, and the temperature of the order of 10 to minus 8 Kelvin, temperature at which it is difficult to detect radiation in the astronomical object. However, calculations made with database of Messier 87 supermassive black hole of 6,200 million solar masses and spin calculated by Tamburini et al. Of the order of 0.9 plus minus 0.05, we obtained results for the temperature of the Messier 87 supermassive black hole of the order of 10 to minus 18 Kelvin and the time of evaporation of the order of 10 to 91 years. These results are more critical than the results obtained with the supermassive black holes studied here. And however, the Event Horizon Telescope obtained the first M87 supermassive black hole image. And that means that for a Schwarzschild and Kerr-Newman supermassive black holes studied here, their detection is also possible because the thermal Hawking radiation is mostly significant compared with the M87 black hole. In all cases, but especially in Reisner-Nordstrom and Kerr, temperature is so low that it makes the supermassive black hole undetectable. However, the mass of supermassive black holes are detected and the quantum effects measured by the entropy formula proposed here, which could be the reason why the Event Horizon was able to get the first M87 black hole photograph despite the insignificant quantum effects, according with the collaborations of Akiyama et al. And in all the cases, just the temperature just above absolute zero, especially in the cases of the Reisner-Nordstrom and Kerr with a surface gravity that tend to infinity to nullity, satisfy the third law of thermodynamics and third law of black hole mechanics. Because the extreme black hole state cannot be reached. Masses decreases during the evaporation process, and the entropy during the evaporation time, entropy with the Bekenstein-Hawking formula and its corresponding event horizon area always decreases individually, but nevertheless the surface gravity and thermal Hawking radiation always increases. For coming research, the time of life of the material content of the supermassive black holes would have to be analyzed from the quantum point of view of the particles that make it up to verify that these are particles that can be detected by a highly sensitive detector such as the Event Horizon Telescope, since the calculations indicate that the time of evaporation is much greater than the Planck constant divided by the mass multiplied by the speed of light squared, for famous formula of Albert Einstein. Conclusions: the entropy formula which we equated with the Bekenstein's generalized second law of thermodynamics allows us to fulfill the objective of elucidating that the intrinsic quantum effects occupy a central role in the compliance with physical laws. Supermassive black holes can be detected despite that the Hawking effect, which reveals their presence, is not significant in this kind of holes. The formula can contribute with the detection of the image of these supermassive black holes, since the detection of this type of holes is directly linked with the insignificance of the intrinsic Hawking effect in obtaining the shadow image of the event horizon of a Messier 87 black hole achieved by the Event Horizon Telescope. These are the references used in this work. Thank you for attending this talk. I'm Leticia Corral from Mexico. Thank you very much.